where we can start from the end of formal practice class that we had on last Friday, and we were analyzing the vertical flight of a rocket, and then also the return to the base. So again, vertically, so everything is happening in a single direction. And we have seen that we have a first part during which we have the, of course, rocket operating, the rocket engine operating. So we have, in this phase, two contributions to the acceleration, which are the force, the acceleration given by the thrust of the rocket and the gravity force. Then at a given point, after 100 seconds, we stop the engine, and the 50 kilograms of left will continue to fly high up to reach the culmination altitude, and then it will start to fall down, and up to a moment when we have to turn again on the rocket and slow the motion and stop the rocket reaching at zero velocity and the zero altitude. So what we have to consider, in general, one important thing that should be examined through this exercise is the role of considering the change of thrust with altitude. So we have a law for changing pressure with altitude, and as a consequence of thrust is linearly dependent on pressure, on ambient pressure. We have a change of thrust with altitude, and in particular, as pressure decreases, we have an increase of thrust. So what happens is that if we assume constant thrust, we have something less in terms of total impulse I provide to the rocket. But from a mathematical point of view, it's easier because we have seen that we can integrate the equation, and we have, let's say, an analytical result. On the other hand, if we consider the change of thrust with altitude, we have no longer an analytical solution, and we should integrate the equations numerically. And this can be easily done, something quite easy. So another third approach is that of considering the starting altitude and the final altitude that we obtain with constant thrust, and we consider the thrust that we would have at that pressure, at that altitude that we have reached considering constant thrust. And so with a second approximation, we take an average thrust, and we, of course, will be something which is totally non-linear, so we cannot assume the average at the minimum and the maximum thrust divided by 2, but at least tell us that in which direction we are going. So I would like to know if someone of you here or remotely has done the exercise, perhaps numerically, and has got the let's say, for instance, the burning time that we need to land, to safely land. Anyone here? So there is just one no. Other people doesn't know if the exercise has been done or not. So I think you should be aware of the fact that you have done or not the exercise. So I suppose that the face looking to me in this way without saying nothing means no. So I assume this. Okay. 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 Anybody from home? Nobody's there. So let's comment. What happens is that, of course, the length of the bird is quite shorter because we have less mass. And so we need a smaller impulse to slow down the rocket. So I don't remember exactly what was the end of last exercise, but of course the part of flight where there is only the gravity force is of course analytical. We have just a constant multiplying. We have that acceleration is constant, and so we have that velocity will change linearly, and so on. So it's easy to get from the final point of the accelerated part to reach the culmination altitude. You just have to consider the fact that velocity goes from a given value to 0, and with the constant acceleration, we have the time. So what we have is that 0 is V1 minus V. So let's say by this T, just trying to avoid to make confusion among the subscripts. And we have here, let's say, G delta T, so that we are sure what we are considering. The time left from V1 to 0 will be a given delta T, and this is V0. We consider constant acceleration of gravity, and so that we can obtain easily the time needed. That is here for the assumption of constant value. It was 2200 Newton. This time is 146 seconds. You have figures on the ladder, the other practice. We had that V1 was 1436 meters per second. Okay, and we had that the altitude was of burnout was 50 kilometers, about 50 kilometers. Okay, this was for constant pressure, constant thrust. So we can also, of course, get the now. So this should be our, if T0 is 0, T1 is 100 seconds, T2 will be 246 seconds. And we should evaluate also now, we have also V1 here. And V2, 0. So the altitudes, I got here 50.119 kilometers. And here I see, of course, we can use now we have that we start from a condition with a given velocity and we have a constant acceleration. So here what we have is that theta 2 will be theta 1 plus v1 t2 minus t1. This will be without acceleration, and then we have minus 1/2 t1, sorry, t2 minus t1 squared. So at this point, the result will be, just replacing in numbers, 155 kilometers. So these are with constant thrust, and we will continue also the constant thrust approach because we have the analytical solution. Now, if you make the integration of the two differential equations, so actually you need integration only for the first part, because here we have analytical solution. So what changes is the starting point for this second leg. And the starting point is with numerical integration is 1, of course, time is for with 100 seconds, and we have v1 is higher, not surprisingly, because we have experienced a higher thrust and we are accelerating so more, and as a consequence also higher altitude. If you compare, you have more or less 6 kilometers difference. Then for the second leg, you can use the same equations. This one and this one with the different values, and you obtain a longer time because we start with a higher velocity. So 2 will be T2 is 268 seconds. That means that the time spent from the burnout to culmination will be 168 seconds. The altitude will be, sorry, the velocity will be 0, of course, and theta 2 will be 194.8 kilometers. Okay. Now let's see what happens once we reach the culmination altitude. At this point, we have, again, a part of trajectory that only considers the gravity force, so just a free fall. And then at a given time, we should light our engine. So in the first part, we will have up to the point when we start the engine is, of course, we start in this case by 0 velocity, and so we have 1/2 time squared. And for the velocity, of course, a linear increase in the negative z direction. The point is that now This would be easy to be computed, but the time t3 is unknown because we have to set this value in such a way that we can slow down up to sea level. So at this point we have to consider, to solve for t3, we need to know what happens later. And so we have also to consider the integration of this for the altitude and velocity in the phase where we have thrust into powered phase. And in this case, we have also to consider the same governing equation as we have seen for the first part, but in this case with different initial conditions. And the difference is that if before we had the initial conditions and we can we have the solution going increasing with time, now we have a problem which is determined by the final conditions. And so if we have the analytical approach, we can try to solve. If we have the analytical solution, we can try to solve, as we need some iterative procedure. So exactly here, the expressions are V4 will be V3 minus G. So this is the analytical solution obtained by considering constant thrust. And you can go back and see that this is exactly the expression that we have used last time. So be careful here. Now we are considering in our descent, we are considering that our M0 is, let's say, M0, let's call it M1. So to avoid confusion, this is the mass that we have at the beginning of operation. So it was the final mass that we have at the former operation of the rocket. And okay, yeah. And next, of course, the other integral was that for the altitude. Is Z3 minus 1/2 G T4 minus T3 squared plus V3 T4 minus T3, and then we have the contribution due to thrust that would be again related to the specific impulse that multiplies T4 minus T3 minus M1 over dot M by the logarithm of the same quantity as above, this one M1 over M1 minus dot M T4 minus T3 . Sì. Sì. È la fase è il punto finale. Suolo, quindi sarà V4 uguale 0 e Z4 uguale 0. Our goal is to reach Z4 and V4 equal to 0 at sea level. Il burning, sempre. Sì, il tempo di running time. I write it again because there is no room here. T4 minus T3 minus dot m, sorry, m1 over dot m, that multiplies logarithm of m1 over m1 minus dot m T4 minus T3, and then we have plus T4 minus T3. So we have these two equations that we have to solve, as I was saying, by enforcing these two conditions. So these two conditions allow us to obtain our the burning time that we need. And in fact, we can obtain, we need to obtain T4 and T3. So the instant, the unknowns are two. One is the ignition time, when we have to ignite the rocket, and the other one is how long we have to keep it burning. So what we do here, this one is simpler, the first one. I can make a substitution here of V3, and at the end have I can solve for T4 minus T3. Okay, I call this tau. So I take this equation here, 1 and 2. I take 1, V3 equal to something that only depends on T4 minus T3. I replace it in here, and as a final result, I have a single equation in tau, T4 minus T3. And the equation is not the equation written without written formally. So we have this expression, which of course is not, we don't have an exact solution. We have also to, not 50, it's m1 minus dot m tau, and minus, and here is tau. Yes. And so I think there is something in terms of, let me check. So it appears to C2 because I used the first relation between v3 and t3 minus t2 minus t2. And I don't know why. Yeah, this is divided by dot m. Should be in this way, so that you have time here and here. This is time by velocity, and this is length. And also here there is some dot m missing. Because this is meter per second. No, it's a length, it's okay. There is no g before. Oh, this is squared. So this is a square length, and no, it's okay. It's okay. This is meter per second squared. So this is second squared, and this becomes meter with this g. So this is the equation. It's equal here, and so we can solve for tau. We can put it in a solver, and we obtain v2 is the culmination altitude, and tau is 28.63 seconds. We can solve for it, and we will solve this equation for putting it here. Of course, m1 is 50, uq is this is 2200, this is 50, this is 50, and this is 1, and the same on the right hand side, and you obtain this value. And the other equation then that we have, that would be obtained by these two equations here. We have a relation that allows us to evaluate also the difference T3 minus T2 from here. So we can obtain V3 putting here 0 and solving for tau, which is this T4 minus T3. We obtain our value of V3. We substitute here, and we obtain also the difference T3 minus T2. Which is or T4 minus T2 is equal to 109.6 seconds. And so we have solved our problem with constant thrust. Then we can compare the results that we have. We already mentioned the condition in 2. We can compare now the condition in 3 and 4 by substituting. Once we know this, we know everything, of course. And so we have that I write first the value with constant thrust, and then in parentheses you see the value determined by integration. So T3 will be 0.5, 408.5 seconds at an altitude of 26.5 kilometers compared to 30 kilometers, and with a velocity V3 1589 with the constant thrust, and will be 1796 considering the bearing thrust. So we have to start slowing down at a higher altitude if we have a variable thrust, and we arrive to this altitude with a higher velocity, and so we have also longer burning time with a higher thrust due to the lower pressure of the ambient. So for the last, so the number in parentheses is the one given by the integration. And the final time, for the final condition, of course, velocity and altitude is 0, so the only quantity is T4, that will be 437.1 seconds compared to 480.9 seconds. If you use the average thrust that you mentioned last time, you will be, let's say, something in between, probably a little bit closer to the integrated value. I have the numbers, but it's not necessary now to show it to you. Okay, so now I invite you again to try simply with MATLAB. You consider 3 different parts, one for each, let's say, for each condition of thrust, of forces, sorry, because you have first thrust, then we have no thrust period, and then we have thrust again. But starting for the equations where we have thrust, you should be careful to this starting point, which is different mass. So the equations are slightly different. And of course, you have to consider the right time from the starting of the engine up to the present moment. But except for of course, what happens is that you have to start an iterative procedure to find the right time. So you have just to play with the 2 times that have to be adjusted to get the right final solution. So finally, we move to another exercise now. This is more straightforward, so we can do it here quickly. Now I would like to make some practice also about staging, and in particular we consider now a launcher with a lift-off mass of 400 metric tons. It is realized to get a delta V of 10 kilometers per second. And it includes similar stages and similar stages, having all characterized by epsilon equal to 0.12, so 12% of inert mass fraction, and specific impulse of 3,000 meters per second. So we will look for the minimum number of stages which is needed to get a payload greater than 4,500 kilograms. So it's actually straightforward. Just have to use the expression that we know for similar stages. And check with different values of n. Sorry? 400T is the lift-off mass. And T is taper metric tons. So actually this is our M0. Are you doing it at home? So similar stages, so we have all the same mass ratios, so the masses are proportional in the different stages. We have the same fractions. So for instance, linear mass fraction is the same for all stages and also for the whole launcher. So we can exploit this expression that in general, of course, I don't mean that we have to recall all the expressions that we obtain. And in general, I will allow you to check with your notes during the exam. You can find on your books, on your notes, what you need. But you have to know what to use. You have to know that it exists or not a relation. And then the other thing that you must know, must be able to do, is to check that your results are sound or not. They make sense or not. So you should be aware to understand if your result can be correct or there is something that is clear that leads to incorrect results. So this is something quite simple. We have that this expression should give us that lambda, which is the ratio mu over m0, and which is 4.5 over, so I say it should be greater than 4.5 over 400. Right? At this point, we have delta V and U Q that allow us to evaluate our mass ratio. And that we can use here in this expression, except for the n. We know epsilon equal to 0.12, so we have that this expression we have this expression that only depends on n. And we can try different values of n. If you try with 1, it's okay, 1? 2? 3? Ti offre di più? 3. 3 is the right answer. So, because with 1, we have a negative payload. With 2, we have 0.6%, which is less than 1.1%. And with 3, we have 1.3%. So we can see here the different masses of each stage just to have an idea, and we can see also some, just for some of the relations. We see, for instance, that we can express for the generic stage the propellant mass as 1 minus E minus dV and UEQ. So this is the delta V of each stage, delta V over N. That for our case is 0.67, or the overall C, which is 1 minus epsilon, 1 minus lambda. There's this value, and I recall that epsilon is the epsilon stage, is 0.12. And so we see that propellant mass fraction of the overall launcher is different from the propellant mass fraction of each stage. If you see the different masses, I can write here M0, MP, MS, MU for the first, second, third stage in total. Yeah, 400 for the first stage, which is the whole rocket. Then it becomes 95.1 tons for the second stage and 22.6 tons for the third stage. Of course, total would be 400. Then for the propellant, we have 268.3 for the first stage, 63.8 for the second stage, and 15 for the third stage. Overall, it will be 347.3. For the unit mass fraction, this is directly related to the propellant mass. Sorry, for the unit mass, this is directly related to the propellant mass in the present assumption. So it will be 36.6, 8.7, 2.1, overall 47.4, and the payload will be, of course, 95.1, 22.6, and 5.4, which is equal to the final payload mass. And you can check for this example if your properties and relation among different stages work. So for instance, you can check by definition, considering the different epsilon of each stage, you can check if the final epsilon is the same. Or we've seen that there is a relation between Z and Zs, which is related to 1 plus lambda stage plus lambda stage squared, and see that you obtain the same result. Okay, let's consider now something without staging, but this time we consider a break, 5 minutes break. I forgot it. No, perché è il minimo, 4.5. Abbiamo qualche cosa in più da portare. No. Allora riprendiamo tra 5 minuti. Just 5 minutes and we resume at 1:15. So we consider now a space vehicle of initial mass of 2,500 kilograms. Initially, we have this is the payload mass of 2,500 kilograms, and then we have also a propellant mass which is more or less like the payload, is 2,700 kilograms, and we know also that we have an inert mass fraction of 10%. So we do a first maneuver where we consume 700 kilograms. Then he would like to evaluate, the problem is to evaluate the residual propellant that we have after a second maneuver this is MP1. That lasts under 20 minutes. And this is done with an engine able to produce 600 newtons and 3,000 meters per second of specific impulse. Okay, so we'd like to see if after this second maneuver we still have some propellant available. Minuti, sì. So you imagine something like Cassini spacecraft making a first maneuver consuming 700 kilograms, and second one lasts under 20 minutes. And we'd like to see if we have some propellant left. No, ci sono 4 di voi che non hanno messo la presenza. Chi altro? Prodigit. Penso, diciamo, lei era presente anche altri giorni, me lo dice adesso? Ah, no, vabbè, per me può essere pure indifferente, però l'hanno fatto tutti, insomma, io non lo so come si fa su Prodigit, magari se lo fa dire a qualcuno dei suoi colleghi. Sì. Sì. Mm. Non ho sentito. Nove sette sette zero sette zero. So this is something I do. I use the symbol ISP for the meaning of specific impulse that can be expressed in meter per second or in second. And this quantity is equal to, if it is expressed in meter per second, it is equivalent, it's equal to the equivalent exhaust velocity, or also effective exhaust velocity. Okay, but the important thing is that we have the meaning. So often you find this in let's say reports and so on. You find specific impulse meter per second. So it's better to have to be relaxed about that. So don't worry if you have the information you need here. E grazie, perché è utile ripetere queste cose. So do you think we have some propellant left, or 560 kg? So it's easy because we know the thrust and specific impulse, so we know the mass flow rate. And if we know the time, the burning time, it means also the propellant mass. So it's simply, we see that we have MP, let's say 2 is MP minus MP1, and this 2000 kilograms. And then we know also that MP3 will be MP2 minus dot MP by TB2, and this is the expression. Of course, you have to write the time in seconds. So this TB2 will be multiplied by 60, and we have that dot m here is 0.2 kilogram per second, and we have of course that dot mp TB2 is equal to 1,440 kilograms. So we have this 560 kilogram left. Given this, we would like now, we haven't used our epsilon, but we can use it to say that we should consider at the beginning, if you like to evaluate the initial mass, it will be the sum of these two plus the inert mass, and the inert mass will be obtained by the propellant mass through the epsilon. So we have that ms is epsilon over 1 minus epsilon mp, and this we have these 300 kilograms more. So overall we have an initial mass which is 5,500 kilograms. We would like now also to evaluate for this second burn. We would like to evaluate the initial and final acceleration, and we would like also to evaluate delta V that can be realized by this available propellant. So how much extra delta V we can realize because of this residual propellant? So this is what we are expected to evaluate. Very simple. It's extremely straightforward. We can evaluate our delta V for the last maneuver starting from the final mass, which is the initial mass minus the propellant mass, and considering the amount of propellant that we have found as residual that give us the initial mass for this maneuver. And so we can just apply our rocket equation, and we obtain 547 meters per second. And about the acceleration, we have that we are assuming constant thrust. Here we are in vacuum, in the deep space. So thrust will always be 600 Newton. And we have to divide by the mass that we have in this case. The question was about the second burn. So we need to consider the initial mass at the beginning of the second burn and at the end of the second burn. So these masses were respectively 4,800 kilograms, and this one 3,350 kilograms. So we have that AI and the F we have these results that would be 0.125 meters second squared and 0.17125 before the 1786 here. Just to have a reference, we can consider this as referred to G0, and we see that they are rather mild accelerations. And go ahead. Okay, if you agree, we move on to another exercise. And it's also a two-step exercise. Let's consider a first part, which is quite fast. Okay, with this, I go ahead. So we would like to calculate this time the specific impulse which is needed to realize a single stage rocket able to provide a delta V of 10 kilometers per second. So we like to calculate this specific impulse to provide this delta V while keeping the liftoff acceleration as 1.25 g and the maximum one equal to 4 times the sea level acceleration of gravity, and we assume constant F. So this is not a question mark. I don't know why sometimes I do something different of what I think. Sorry. Okay. Yes. Sorry. So here the trick is to exploit the fact that if we have constant thrust, giving the ratio between initial and final acceleration is equivalent to give the mass ratio. So once we have the mass ratio, of course, we can use the rocket equation. So we say AI over AF is equal to 0.3125. And well, what we need actually is the maximum acceleration was 4 times the gravity force. So again, we can reach this limit if we have a mass ratio of 0.315, 0.3125, and finally UE is equal to delta V over logarithm of one over mr, and as a consequence you obtain this specific impulse in meter per second, or the quantity told by your colleagues if you write it in seconds. So let's now assume so actually any mass ratio greater than this means that the final acceleration will be less than 4g. If we now pass to the second part of this exercise, where we assume that the same minimum and maximum acceleration, as we have seen here, must be obtained with a vehicle which is characterized by I'm just checking something. Yes. which is characterized by lambda equal to 0.1 and epsilon equal to 0.1. So we see now that we have this vehicle. We still have to respect these constraints in terms of acceleration, and the further information we have is that this vehicle has 9 equal engines, 9 units of the same engine. So the question is, at what time we have to shut down at least one engine to avoid exceeding the maximum acceleration? And then the second question is, how many engines must be shut down before the end of operations? Because of course we know that if we shut down the engine, we don't change the delta V, at least in the ideal model, but we reduce the acceleration because we reduce the force, the thrust, whereas we have the same specific impulse, the same propellant consumption per each engine. So overall, the propellant consumption in terms of specific impulse or ratio between thrust and mass flow rate will always be the same independently of the number of engines, but the thrust level will change depending on the number of engines that are operating. So from this information, the initial information, we can we know here this is not a datum of the problem. This was for the first part. What we know now is this one. This lambda, this epsilon, this delta V, H0 and AF. So, and this N. These are the new data that we have. La seconda richiesta è quanti motori devono essere spenti all'istante finale, sempre per rispettare il vincolo dell'accelerazione. Dopo quanto tempo bisogna spegnere il primo e quanti alla fine? Nel tempo bisognerà spegnerne più di uno. So during operation we have to shut down more than one engine, because we shut down one when we reach 4G, then we start to accelerate again, and we reach again 4G and shut down another, and so on. If we like to keep, let's say, to have always the maximum thrust and be below the maximum allowable acceleration. So probably will not do that, but in general, if you like, these are the limiting conditions. Of course, this is a nuclear rocket, and also in this case, there will be something like this. So first of all, you recall that if you have lambda and epsilon, you also have the mass ratio. And so once you know delta V and mass ratio, you also know the specific impulse. When we are looking for the time such that with f equal to f0, we should have that the acceleration is kept below the maximum value. And the acceleration as a function of time can be expressed as the ratio between the thrust divided by the decreasing mass that we have. And at this point we can elaborate this expression, exploiting the fact that we can express everything in terms of acceleration and specific impulse once we consider that our f0 is related to m0. So here I can divide everything by numerator and denominator by m0, and everything more or less cancels. I do it. So we can use here this relation and here is again the initial acceleration. So looking to this expression, I can bring this here. And we can solve for t. Solving, you obtain this expression. T less than UEQ, during source velocity, 1 over AI minus 1 over AF. And so the result is that time is 337.7 seconds. And even easier is the case of the final condition, the condition at the end of operation, because at this point we have, we know that we have the final mass, and this will be related to the initial mass to the mass ratio that we have already computed in terms of lambda and epsilon. So given lambda and epsilon, we have the mass ratio. Once we have the mass ratio, we have the final mass. And so we have to know how many fraction of the initial thrust will be related to this final mass. So in practice, we have that AF over 0 is equal to the thrust we have, let's say, a fraction of the initial thrust that we have at the last instant divided by this final mass. And this final mass is mr m0. And this is the final acceleration that must be less, let's say, of so I don't know why I'm using this G. This is FMA. This is not existing. Okay. And well, at this point we can evaluate our X. Must be less than F over M. F0 over M0 is AI. So we have that this must be MR maximum acceleration over the initial one. And this will be the result. So it means that this X, let's say N, let's assume N equal X and 0, it comes at N0 is 9, and N must be less than 5.472. And so it means that we have that maximum number of engines that must be ignited at burnout is 5. And so we have to shut down at least 4 engines. So this concludes today's practice. And just information that I have to give you is that on next Wednesday, 17, there will be no class. The class of the Wednesday afternoon of next Wednesday is cancelled, or better, it will be, of course, as I mentioned at the beginning, there will be some classes that will not be given, and that will be, of course, we have some days available in May that during which we can recover the missing classes. So this will be the case of next Wednesday. I stop recording here.